Even the nearest star feels close on a map of the galaxy, yet in the real scale of space, it remains almost unimaginably far away. Proxima Centauri is the closest sun beyond our own, but with today's fastest spacecraft, the journey would still take thousands of years. This video explores the true size of that distance, the brutal limits of speed and energy, and the quiet reason the stars may remain forever beyond human reach. If this kind of deep space journey fascinates you, please like the video and subscribe to the channel. The sun does not sit in a crowded cluster of bright stars. It drifts through a quieter part of the Milky Way, inside the broad stellar disk, among scattered neighbours separated by immense reaches of dark space. From Earth, the night sky can appear richly filled, but that appearance is shaped by distance and perspective. Many of the brightest stars visible to the eye are not especially near. Some are large and luminous and can be seen across long spans of space. The stars that truly live closest to the sun are often smaller, dimmer, and far less conspicuous. The local stellar neighbourhood is therefore calmer and more thinly populated than the sky first suggests. It is a region of long intervals between stars, where even the nearest neighbour remains astonishingly far away. Astronomers often speak of the solar neighbourhood to describe the region around the Sun that can be studied in fine detail. It is not a sharp-walled place. It has no visible boundary in space. It is simply the nearby part of the galaxy, the area where distances are small enough by galactic standards for individual stars, motions, and local structure to be measured with high precision. In that neighbourhood, the Sun is one ordinary star among many ordinary stars. It is neither at the centre of any local arrangement nor in a specially dense zone. It belongs to a vast rotating galaxy and occupies a modest place within one of its spiral-armed regions. Around it lie red dwarfs, orange dwarfs, white dwarfs, occasional brighter stars, brown dwarfs too faint to shine as true stars, and clouds of thin gas and dust spread through the interstellar medium. At the widest local scale, what defines this neighbourhood is not abundance but spacing. Stars are numerous in the Milky Way as a whole, yet they are still separated by distances so large that each one sits almost alone. If the Sun were imagined as a small object placed in an open landscape, the next stars would not stand nearby like trees in a grove. They would lie far off across a nearly empty plain. This is the first physical truth of the local stellar environment. Space between stars is not packed with suns. It is mostly space. There is gas, dust, magnetic field, and energetic particles. But the density is so low that a human understanding shaped by air, water, and solid ground does not easily match it. The nearby galaxy is sparse. The Sun also moves through a local setting shaped by older stellar events. It lies within a region of unusually thin hot gas often called the local bubble, a cavity thought to have been carved in part by ancient supernova explosions. The surrounding medium is irregular, patchy, and dynamic, with denser clouds in some directions and thinner stretches in others. The solar neighbourhood is not only a map of stars, it is also a volume of interstellar matter with structure, temperature, and motion. The Sun and its planets travel through this environment as the galaxy turns, carrying the heliosphere through a medium that is thin but real. Most nearby stars are not large blue stars or giant stars. They're red dwarfs, small cool stars that burn slowly and faintly. This matters because the nearest part of the galaxy is not organised around spectacle. It is organised around what is common. The most common stars in the Milky Way are small and dim, and the Sun's neighbours reflect that rule. Many nearby objects are so faint that they are invisible to the unaided eye, even though, in cosmic terms, they are close. This gives the local region an interesting contrast between reality and appearance. The eye sees a dramatic sky of bright points scattered across a dome, while measurement reveals a quieter three-dimensional arrangement dominated by modest stars that attract little attention from the ground. The geometry of this neighbourhood is also more layered than the night sky suggests. Constellations create the impression of patterns on a flat surface, yet the stars that seem grouped together can stand at very different distances. In the local region, depth matters more than pattern. Each star follows its own orbit around the centre of the galaxy. Each has its own speed, direction, age, mass, and history. Some pass nearer to the Sun over long spans of time, and some move farther away. The nearest star today is not guaranteed to be the nearest star forever. On timescales of tens of thousands of years and beyond, the solar neighbourhood slowly rearranges itself. Astronomers measure this nearby region through parallax and stellar motion. Parallax is the tiny apparent shift of a nearby star against the far background as Earth moves around the Sun. These methods turn the seeming flatness of the heavens into a measured volume. They show that the Sun's closest stellar company occupies a region only a few light-years across. Yet even that phrase can mislead by sounding modest. A light-year is the distance light travels in 1 year, because light itself moves with unmatched speed through vacuum. A light-year is an immense unit. When several light-years separate neighbouring stars, the ordinary meaning of nearby begins to break down. This is why the local stellar neighbourhood carries two truths at once. On the scale of the Milky Way, it is intimate. The galaxy stretches across about 100,000 light-years, so stars only a few light-years away count as immediate neighbours. On the scale of travel, matter, and human experience, the same distances are severe beyond intuition. The Sun is not marooned at the edge of the universe. It lives inside a normal galactic district with many neighbouring stars. Yet those neighbours are not close in any everyday sense. The local region is gentle, familiar to astronomy, and mapped with increasing precision, but it is built on immense separations. So the first outer layer of this subject is simply the nearby star field itself. The Sun inhabits a quiet portion of the Milky Way, inside a sparse stellar environment shaped by long distances, faint common stars, thin interstellar matter, and slow galactic motion. What seems from Earth like a richly crowded sky resolves, under measurement, into isolated suns scattered through a large dark volume. The nearest stellar neighbourhood is local only by the standards of a galaxy. By every smaller standard, it is already vast. Within this local region, the Sun occupies no central throne and no protective ring of nearby stars. It is one ordinary yellow dwarf moving through the galaxy with its own orbital path, embedded in a neighbourhood where even the closest stellar company stands at distances far beyond any familiar measure. In the immediate sense, the Sun is solitary. The planets remain bound to it. Comets drift in long, cold paths around it, and small bodies fill the outer reaches of the solar system. But beyond that dominion there is no next star waiting just outside the last planet. There is only the long outward thinning of the Sun's own influence, and then the much larger darkness between one star and another. The heliosphere, the broad bubble formed by the outward flow of solar particles, extends deep into surrounding space, but it does not bridge the gap to another star. It is a local envelope, not a road. Beyond it lies the interstellar medium, thin and diffuse, and beyond that, still far off, the nearest stellar systems begin. This spatial arrangement matters because it reveals how misleading the word neighbour can be when carried from human life into astronomy. On Earth, A neighbour is separated by meters, perhaps by a road, perhaps by a field. In the Sun's environment, a neighbour is separated by trillions of kilometres. The term survives, but its ordinary feeling does not. The nearest known stellar system to the Sun is the Alpha Centauri system. Its faint red component, Proxima Centauri, lies a little more than 4 light-years away, while the brighter pair, Alpha Centauri A and Alpha Centauri B, lie slightly farther still. By galactic standards, this is close. By any standard tied to travel, time, or machinery, it is immense. Light itself, moving at the fastest speed known in nature, requires more than 4 years to cross that interval. Nothing with mass can travel faster than light, so every real journey must take longer. The nearest stars are therefore not nearby in any practical sense. They are merely the least distant among distances that already exceed intuition. This is the central reality of the Sun among its neighbours. The stars near it are not crowded around a luminous centre as planets gather around a star. They are independent suns, each with its own gravity, motion, and history, scattered through a shared galactic volume. The Sun does not illuminate them in any significant way, and they do not illuminate it. Their gravitational pull on the solar system exists, but at these distances it is weak compared with the binding force of the Sun over its own planets. Each star rules only a small local dominion, and between those dominions lies an enormous region where no star is close enough to dominate the scene. The nearest stars are also not arranged in a static pattern. Each one moves around the Milky Way with its own velocity. Over long intervals, the list of nearest neighbours changes. Some stars drift slowly closer, others recede. The Sun itself is in motion as well, circling the galactic centre over hundreds of millions of years. So the local map is not frozen. It is a slow choreography of separate bodies crossing a thinly populated region. Yet even though the arrangement changes, the spacing remains the defining feature. The stars do not approach one another until they become a close-packed swarm. They remain far apart, and the quiet emptiness between them remains the governing fact. The contrast with the solar system is severe. Inside the solar system, even the outer planets still belong to a common family under the Sun's control. Light from the Sun reaches them in hours, not years. Signals sent by spacecraft take minutes or hours to travel across the planetary region. Distances there are already challenging by human standards, yet they still form a compact structure compared with the gap to the nearest star. Once the solar system is used as a measuring stick, the next star is revealed not as the next step outward, but as an altogether different order of separation. The outer edge of the Sun's planetary system, however defined, does not lead naturally into the beginning of another star's system. It leads into a vast interval. This is why the nearest stellar company feels both local and unreachable. Astronomy classifies the Sun as part of a nearby set of stars because the galaxy is so large. A star 4 light-years away is indeed close when compared with regions hundreds or thousands of light-years distant. But a map that serves astronomy does not serve travel in the same way. The Sun's neighbours are near enough to be measured precisely by parallax, proper motion, and spectroscopy, yet still too far for any human journey to treat casually. The nearby stars can be catalogued, characterised, and compared. Their distances can be turned into exact values. Their masses, temperatures, and motions can be studied. None of that reduces the emptiness between them. The Sun's immediate stellar company is also dominated by small stars rather than bright grand ones. This means that the nearest neighbours are often dim red dwarfs, physically modest and faint in visible light. Some nearby objects are brown dwarfs, too small to sustain the full hydrogen-burning process that defines a star. The local environment is therefore not only sparse but subdued. It is not a brilliant court surrounding the Sun. It is a wide region inhabited mostly by quiet, common objects. That quietness reinforces the feeling of isolation. The Sun is not pressed among giant beacons. It lives among distant, often faint companions separated by the dark volume of interstellar space. So when the Sun is placed among its neighbours, the essential point is not merely which star comes first or second in distance. The essential point is scale. The nearest star is not just somewhat farther away than the outer planets, it is incomparably farther away. The Sun's immediate neighbourhood, when seen as a three-dimensional physical reality rather than a pattern on the sky, is a region of scattered suns with enormous separations between them. This is the first narrowing of the subject. The galaxy has already become the neighbourhood. The neighbourhood has already narrowed to the Sun, and the Sun's nearest company has already shown the problem in its simplest form. Even here, at the closest possible stellar edge beyond the solar system, distance is already almost beyond practical reach. The nearest star system beyond the Sun is not a single star standing alone in darkness. It is a small stellar family, a three-body arrangement known as the Alpha Centauri system. From Earth, it appears as one of the most familiar bright objects in the southern sky. Yet that bright appearance hides internal structure. What seems to the unaided eye like one star is, in physical reality, a more intricate arrangement. Two stars form a close bright pair, Alpha Centauri A and Alpha Centauri B, while a third faint red star, Proxima Centauri, lies much farther from them and moves as a distant member of the same broader system. The nearest star system is therefore not a solitary beacon, it is already a layered place. Alpha Centauri A and Alpha Centauri B make the dominant central pair. They orbit one another in a long gravitational dance, circling a shared centre of mass over many decades. Alpha Centauri A is somewhat like the Sun, though a little more massive and more luminous. Alpha Centauri B is smaller, cooler and dimmer, with an orange tone rather than the Sun's yellow-white light. Together they form a binary star, meaning two stars bound by gravity and revolving around one another. Binary systems are common in the galaxy. In that sense, the nearest stellar destination is not unusual. It reflects a wider rule of the Milky Way, where many stars are born and remain in pairs or larger groups rather than in isolation. The orbit of the central pair is not a perfect circle. It is an ellipse, so the stars move closer together and then farther apart over the course of their cycle. At their nearest, they are separated by a distance comparable to the scale of the outer solar system, and at their farthest they are much more widely parted. Even so, they remain clearly part of one tight central system. Their mutual gravity dominates their local arrangement. They shine brightly enough that, from nearby space, each would strongly influence the conditions around the other, not by touching but by sharing a common gravitational environment. Any planets in stable orbits around either star would belong not to an isolated sun but to a dynamic binary setting. Around this close pair lies the third member, Proxima Centauri. Proxima is much fainter than the other two and far smaller. It is a red dwarf, one of the common low-mass stars that fill much of the galaxy. It does not sit close beside Alpha Centauri A and B in the way the two bright stars sit close to each other. Instead, it lies at a very large distance from them, orbiting so far out that its period around the central pair is measured not in years or decades, but in vast spans of time. This is why the nearest star system is not simply one compact arrangement that can be pictured on the scale of a household model. It is a nested system, tight at the centre and extremely extended at the edge. This wide layout matters because it changes the meaning of arrival. To say that a spacecraft reaches the Alpha Centauri system would not yet specify where it has actually gone. Reaching the broad gravitational domain of the system is not the same as approaching one of its stars closely. The system contains internal distance on a huge scale. Alpha Centauri A and B form one local region. Proxima occupies another, much farther out. The nearest stellar system is therefore already a reminder that astronomy works in layers. Even when the destination is named, the destination is still larger and more divided than ordinary language suggests. The physical character of the three stars also gives the system a quiet complexity. Alpha Centauri. A resembles the Sun enough to draw attention as a possible host for planetary environments, not entirely unlike the inner parts of the solar system. Alpha Centauri B, being cooler and somewhat smaller, offers a different stellar climate. Proxima, as a red dwarf, belongs to a class of stars known for faint light, long lifetimes, and magnetic activity that can affect any nearby worlds. These differences mean that the nearest star system is not one place in a simple uniform sense. It is three related stellar environments under one gravitational umbrella, each with its own light, temperature, and rhythm. From Earth, the system also teaches an important lesson about appearance and reality. The bright pair stands out in the southern sky, and has done so for human observers for a very long time. Yet its true arrangement only emerges through careful measurement. Telescopes, positional astronomy, spectroscopy, and orbital analysis reveal that the visible point is a binary, and that the faint red companion belongs to the same larger family. This is a common pattern in astronomy. The sky offers a compressed image. Measurement unfolds it into depth, motion, and structure. The Alpha Centauri system, though nearest, still has to be discovered layer by layer. Its nearness by galactic standards has made it a natural object of study. Astronomers have measured the masses of the stars, followed the orbit of the central pair, studied the activity of Proxima, and searched for planets within the system. This attention does not come only from curiosity about another star. It comes because Alpha Centauri stands as the first outward step beyond the Sun in any realistic map of interstellar space. It is the nearest full stellar setting in which comparison becomes natural. There is the Sun and its family, and then, after the long dark interval, there is Alpha Centauri and its threefold arrangement. Yet even at this stage, before the subject turns to the closest single star or to the meaning of interstellar distance in detail, the system already carries the central emotional truth of the larger topic. Nearness does not bring familiarity in the ordinary sense. The nearest external star system is not close enough to feel adjacent, not simple enough to feel singular, and not small enough to feel immediately knowable as one object. It is a real place, a gravitationally connected family of stars, but it remains remote, layered, and internally vast. So the third region of this journey settles on the Alpha Centauri system itself. It is the nearest stellar system to the Sun, built around the bright binary of Alpha Centauri A and Alpha Centauri B, and extended outward to the faint red dwarf Proxima Centauri. It is a compact center with a distant outer member, a familiar bright point that resolves into multiple suns, and a destination whose very structure shows how quickly space becomes large. Before any journey can even begin in thought, the nearest system already proves that the next place beyond the Sun is not one star waiting at the edge of darkness, but a spacious and divided system of its own. Within the broader Alpha Centauri system, one star stands slightly closer to the Sun than all the others. That star is Proxima Centauri. It is not the brightest member of the system, nor the largest, nor the one that first captures the eye in the night sky. In visible light it is faint, small, and easily overlooked, yet in strict distance it is the nearest known individual star beyond the Sun. This gives it a special place in human thought. Whenever the mind begins to picture another star as a destination, it almost always arrives first at Proxima. The nearest point beyond the solar system gathers attention not because it seems easy to reach, but because it defines the minimum distance any true interstellar journey must cross. Proxima is a red dwarf, a small cool star of the kind that fills much of the Milky Way. Red dwarfs are the most common stars in the galaxy, and Proxima represents that ordinary majority far better than the brighter stars, Alpha Centauri A and Alpha Centauri B. It carries only a fraction of the Sun's mass and shines with only a tiny fraction of the Sun's visible brightness. Its surface temperature is lower, its light is redder, and its total power output is far weaker. If the Sun vanished and Proxima took its place, Earth would not remain warm and bright. The familiar planetary environment would be transformed into a far colder and darker one. Proxima is therefore nearest not only in distance but also in contrast. The nearest star is not another sun, it is a much smaller and dimmer object. This smallness shapes the star's character. Proxima burns fuel slowly and can endure for spans far longer than the life of the Sun. Small stars are economical stars. They consume their hydrogen at a measured rate and remain stable for immense stretches of cosmic time. Yet small does not mean quiet in every sense. Proxima is also known for magnetic activity. It can produce flares, brief outbursts that release energy across the spectrum and alter the conditions around the star. This is one reason astronomers study it closely. The nearest star is not only close by galactic standards, it is also a living example of the most common kind of star in the universe, a type whose modest size hides a more complicated local environment. The distance to Proxima is often given as a little more than 4 light-years. That phrase is so familiar in astronomy that it can seem mild, almost manageable. But the gentleness of the words hides the severity of the fact. A light-year is the distance light travels in 1 full year through vacuum, moving at the fastest speed known in nature. To say that Proxima lies a little more than 4 light-years away is to say that even light, which circles Earth many times in a single second, needs more than 4 years to cross the gap. Nothing with mass can match that speed. Every actual craft must travel more slowly. The nearest star is therefore not near in the ordinary meaning of the word. It is only the least distant member of a class of objects already separated from the Sun by enormous intervals. This is why Proxima carries such an unusual role in thought. It serves both as the nearest possible destination and as the first clear demonstration of interstellar remoteness. It is the smallest number in a category where the numbers are already overwhelming. If the nearest star were only slightly beyond the outer planets, then interstellar travel would be a difficult extension of deep space travel. But Proxima is not slightly beyond the planets. It is far beyond the entire familiar architecture of the solar system, the giant planets, the Kuiper belt, the distant scattered bodies, and the broad cloud of icy objects that may surround the solar system all remain part of one star's domain. Proxima lies outside that domain by an immense margin. Between the Sun and Proxima there is no stepping stone world, no chain of moderate intervals, and no natural bridge. There is only the interstellar gulf. Because Proxima is faint, it also reveals something important about the nature of cosmic neighborhoods. The nearest external star is not the most prominent one in the sky. Human sight is drawn to brightness, but physical nearness and visible brilliance are different things. A star can be very close and still faint if it is small and cool. Proxima demonstrates that rule with unusual clarity. It is physically near on the scale of the galaxy and yet visually modest. The nearest star does not announce itself with grandeur. It has to be found through measurement, through telescopes, through careful astronomy. Nearness in space does not guarantee presence in human perception. Proxima also has planetary interest. Observations indicate that at least one planet, Proxima b, orbits within a region where liquid water might be possible under the right conditions, though the actual environment on that world remains uncertain. Additional candidate worlds have also been discussed in the scientific literature, with varying levels of confidence. These possibilities add to Proxima's importance as a target of observation. The nearest star is not merely a distant ember in darkness. It may also host planets, and that possibility strengthens its symbolic role as the first other sun that can be studied as a system with local worlds of its own. Yet even that added interest changes nothing about the governing fact of distance. A planet around the nearest star is still a planet around a star more than 4 years away at the speed of the light. Signals themselves reveal the slowness built into this relationship. A message sent from Earth toward Proxima would not arrive in months or days. It would take more than 4 years to get there, and any reply would require the same in return. A simple exchange would therefore span more than 8 years under the impossible assumption that a receiver there answered at once, before any spacecraft is imagined. The time delay in light alone already changes the meaning of contact. The nearest star is close enough for astronomy and too far for immediacy. It belongs to the reachable universe only in the abstract sense that its light arrives here. In every practical human sense, it remains remote. So Proxima Centauri becomes the first precise edge of the interstellar problem. It is not a broad system name now, but a single star, the closest known one beyond the Sun. It is small, dim, long-lived, magnetically active, and modest in appearance. It may have planets. It is part of the Alpha Centauri family while still standing at a large distance from the brighter central pair. Most of all, it is the nearest possible destination and already far beyond any distance that human intuition treats as neighbouring. The path to any other star begins here, and it begins with a truth that does not soften under repetition. The nearest star is still very far away. The distance to the nearest star begins to feel real only when the mind stops treating it as a phrase and starts treating it as a measure. Until then, the words can remain strangely soft. A light year sounds almost poetic, as if it names brightness or duration rather than distance. In astronomy, however, a light year is a unit of length. It means the distance that light travels through vacuum in 1 year. Because light moves faster than anything else known in nature, this unit is enormous. It is used not because astronomers enjoy abstraction, but because ordinary units become awkward when stars are involved. Kilometers are still valid, but the numbers grow so large that they stop helping intuition. The light year is the first attempt to give distance between stars a form that can still be spoken. Even so, the light year does not immediately solve the problem of understanding. It compresses a huge fact into a manageable phrase, and in doing so it risks making the fact seem smaller than it is. To say that Proxima Centauri is a little more than 4 light-years away is accurate, but accuracy alone does not make scale familiar. The phrase does not easily carry the full meaning that light itself, moving at the greatest possible speed, requires more than 4 years to make the crossing. The nearest star does not lie a few days away for light, or a few weeks away, or even a few months away. It lies more than 4 years away at the speed limit of the universe. This is the first serious use of the measure. It is not merely a label, It is a warning about scale. Human experience is poorly built for such distances. On Earth, large journeys are measured in hours or days, across oceans. Even the older age of travel remained inside the frame of a single life lived at ordinary pace. Inside the solar system, by contrast, distance begins to detach from everyday understanding. Light from the Sun reaches Earth in a little more than 8 minutes. That same light reaches Jupiter in tens of minutes, and Neptune in several hours. Already, within one planetary system, the scale has shifted far beyond ordinary geography. Yet even Neptune remains close when compared with the nearest star. The whole planetary structure around the Sun occupies a compact region beside the interstellar gap. Astronomy often uses the average distance between Earth and the Sun as a smaller reference step. This is called an astronomical unit. It is helpful inside the solar system because planetary orbits are naturally compared with Earth's orbital distance. Mercury lies much closer to the Sun than one astronomical unit, while Jupiter lies several times farther away, and Neptune much farther still. With this scale, the solar system acquires a readable order. The planets are not nearby in any human sense, but they are placed within a common family of distances that can be described and compared. The problem arises when that family is set beside the distance to another star. Then the familiar order suddenly shrinks. If the Earth-Sun distance is taken as one step, Proxima Centauri is not a few hundred such steps away. It is tens of thousands of them. The interval is so large that the inner planets disappear into insignificance, and even the giant planets no longer seem far. Jupiter, for all its grandeur, remains close to the Sun in interstellar terms. Neptune, which once marked the outer majesty of the known planetary order, is still very near the centre when compared with the distance to Proxima. The nearest star is not just beyond the last planet, it is beyond the entire main architecture of the solar system, by a margin so great that the planetary region begins to look like a small inner court within a far larger empty estate. The comparison grows even more severe when the outer icy regions are considered. Beyond Neptune lies the Kuiper Belt, a broad population of frozen bodies and dwarf planets. Beyond that lies the scattered disk, where some objects follow elongated and tilted paths shaped by the long history of planetary interaction. Farther still, at least in strong theoretical expectation, lies the Oort cloud, a vast spherical reservoir of icy bodies extending far from the Sun. This remote cloud marks one of the furthest conceptual edges of the Sun's gravitational domain. Yet even this enormous surrounding structure, if described at its broadest likely scale, still does not erase the larger truth. The nearest star remains beyond it. The gap between the outer edge of the Sun's long reach and the beginning of another star's region is still substantial. Even after the solar system has been expanded to its most remote halo of icy objects, the stars do not suddenly touch. This is the point at which the light year becomes more than a technical convenience. It becomes the only honest language for the problem. A distance measured in kilometers is exact but numbingly large. A distance measured in astronomical units is more relatable inside the solar system, but still becomes cumbersome between stars. The light year says plainly that the gap belongs to a different class of scale. It measures not only separation in space but also the travel time of light, which is the fastest thing there is. In that sense, every light year quietly contains a clock. It says how long a beam would need, how long a signal must wait, and how long every slower object would fail to match. That is why the nearest star system is so unlike a farther planet. Mars can be reached in months. The giant planets require years for robotic missions. Even the most distant probes humanity has launched, after many decades, have only begun to move through the outermost region of the Sun's influence. These spacecraft are extraordinary achievements, yet in terms of the nearest star they have barely started the larger journey. The difference is not simply one of more fuel or more patience. It is a shift in category. Planetary distance can still be treated as internal travel within one star's household. Interstellar distance is the crossing from one household to another, with a vast dark tract in between. So the fifth region of this subject is a lesson in measure. A light year is a distance, not a period of time, and it is used because the gap between stars is too large for smaller units to remain intuitive. Once that measure is understood, the nearest star changes character. It ceases to seem like the next place after Neptune or the next stage after the outer planets. It becomes what it truly is, a destination separated from the solar system by a distance so great that even light needs years to make the crossing. The language of neighborhood survives in astronomy, but measurement strips away its comforting illusion. The nearest star is close only on the scale of a galaxy. On every smaller scale, it is profoundly far. Between the Sun and the nearest star there is no solid road, no chain of islands, and no perfect void. The region between stars is often spoken of as empty space, and in one broad sense that is true. It is empty when compared with the crowded densities of planets, atmospheres, oceans, or stellar interiors. Yet it is not empty in the absolute sense. Interstellar space contains matter, though very little of it, and that sparse matter changes the meaning of the journey. A traveller leaving the solar system does not enter nothing. It enters an environment so thin that human instincts struggle to recognize it as an environment at all, yet real enough to shape motion, exposure, and survival across long durations. This medium is made mainly of gas, with a smaller contribution from dust. The gas consists largely of hydrogen, the most common element in the universe, along with helium and trace amounts of heavier elements. Much of it is so thinly spread that a vast volume of space contains only a small number of particles. Near Earth, air presses on every surface and fills every breath. In interstellar space, the particle density can fall to levels so low that even the best earthly vacuum chamber seems crowded by comparison. But thin does not mean absent. Over very long paths, even a sparse medium becomes significant. The journey to another star is not a leap through absolute nothingness. It is a passage through a nearly transparent sea. Dust adds another layer to this sea. Interstellar dust is not like household dust drifting in sunlight. It consists of tiny solid grains, often made of silicates, carbon-rich compounds, or frozen coatings in colder regions. Each grain is extremely small, but the grains matter because they interact with light and motion in ways gas alone does not. Dust dims and reddens starlight over long distances. It marks the presence of structure within the galaxy. It also becomes a hazard for a fast-moving spacecraft, because even a tiny grain carries destructive energy when struck at extreme speed. So the darkness between stars is not just dark. It contains fine material that can scatter light, trace magnetic structures, and threaten any object crossing the gap quickly enough. The interstellar medium is also not uniform. It has regions of different temperature, density, and composition. Some parts are relatively warm and thin. Some are cooler and denser. Some are ionized, meaning electrons have been separated from atoms so that the gas contains free charges. Some are more neutral. The Sun moves through one local setting today, but that setting is only a small portion of a larger galactic patchwork. Clouds, cavities, shock fronts, and old stellar outflows all help shape the nearby medium. This makes the space between stars less like a featureless blank page and more like a faintly textured field. The texture is subtle, but over interstellar distances, subtle structure matters. Magnetic fields thread through this medium as well. They are weak compared with the magnetic fields of planets or neutron stars, but they extend across broad regions of the galaxy and influence the motion of charged particles, because some of the gas is ionized. The interstellar medium does not behave like a simple neutral mist. It behaves partly like plasma, a state in which charged particles respond to magnetic and electric forces. This means that the space between stars has invisible architecture. Particles spiral, streams are guided, and shock waves from stellar events can leave lasting marks. To human senses, this architecture is hidden, but to physics, it is present. The gulf between stars is not only material, it is electromagnetic. Radiation moves through this medium from many sources. Starlight crosses it. Ultraviolet radiation from hot stars alters it. X-rays and cosmic rays pass through it. Cosmic rays are high-energy particles, many of them protons or atomic nuclei, moving through space at extreme speeds. Some come from the Sun, but many originate far beyond the solar system, accelerated by violent processes such as supernova remnants and other energetic astrophysical environments. The interstellar medium therefore carries not only sparse matter, but also a constant bath of energetic particles and radiation. A spacecraft between stars would not drift in a calm black silence. It would travel through a region of continuous exposure, receiving impact from matter at one scale and radiation at another. At first, this environment seems too thin to matter. A single cubic centimetre of interstellar space may contain very few particles, so the human mind is tempted to dismiss the whole region as negligible. But the journey to another star is not measured in centimetres. It is measured in trillions of kilometres. Over such lengths, a medium of low density can still accumulate effects. Gas can erode, dust can strike, radiation can damage. Tiny interactions repeated over vast durations become important. What seems almost non-existent at a glance becomes decisive when multiplied by years of travel and immense distance. This is one of the recurring truths of interstellar space. It is not density alone that matters, but density multiplied by path length and time. The interstellar medium also places a boundary around the solar system itself. The outward flow of charged particles from the Sun forms the heliosphere, a protective bubble of solar influence. Beyond that bubble lies the local interstellar medium more fully, pressing back against the solar wind. The edge between the two is not a hard shell, but it marks a change in regime. Inside, the Sun still dominates the flow of charged particles. Beyond, the wider galactic medium takes over. The crossing made by the Voyager probes reveals this transition as a real physical shift rather than a poetic idea. To move toward another star is therefore not only to move farther from the Sun, it is to leave one plasma environment and enter another, broader one. This larger environment is also slow in a way that planets are not. Inside the solar system, the dominant features are the Sun, the planets, and the paths of bodies bound to them. In the interstellar medium, motion is more diffuse. Clouds drift. Shock waves pass over long ages. Magnetic patterns evolve. Radiation fields vary with region and source. The medium is not still, yet its changes often belong to timescales larger than a human journey would easily grasp. A spacecraft would travel through a place that is both dynamic and eerily quiet, active in physical terms but almost empty to the eye. So the sixth region of this subject is the dark gulf itself, understood not as a blank absence but as a real though exceedingly thin environment. Between the Sun and the nearest star lies gas, dust, plasma, magnetic field, and radiation. The density is low beyond everyday comparison, but the path is so long that this thinness does not erase consequence. Interstellar space is not an obstacle because it is crowded. It is an obstacle because even its faint substance becomes meaningful across enormous distance. The traveller who leaves the solar system does not escape environment. It merely enters one so sparse and so prolonged that difficulty takes on a different form. Once the space between stars is understood as a real medium rather than a perfect void, the problem of travel begins to take on its next form. The central issue is motion itself. A destination more than 4 light-years away cannot be approached in the same spirit as a journey across a continent, across an ocean, or even across the planetary region around the Sun. At that scale, motion is not simply movement through space. It is a long argument between speed and duration. The gap is so large that the journey becomes defined less by departure and arrival than by the prolonged stretch in between. Even before questions of engineering, fuel, or survival are raised, simple motion across the gulf already reveals why the nearest star remains so remote. In ordinary experience, speed shrinks distance. A fast vehicle makes a city seem near. A faster aircraft makes a continent manageable. The mind therefore learns to treat higher speed as a general solution. In interstellar travel, that habit begins to fail. The distance is so vast that speeds which seem extraordinary by human standards remain small by the standards of the journey. A machine can move faster than any aircraft ever built, faster than any projectile crossing Earth, faster than any object commonly imagined in everyday life, and still remain slow when judged against the gulf between the Sun and another star. Interstellar space changes the meaning of fast. The natural comparison is light. Light crosses the distance to the Moon in a little more than a second and reaches the Sun from Earth in a little more than 8 minutes. These intervals already seem swift beyond instinct. Yet the nearest star lies more than 4 years away even for light. This means that the usual comfort associated with speed disappears at once. Any object with mass must travel more slowly than light. Therefore, every possible craft, no matter how advanced, must require longer than light does. Once this is grasped, the scale of the problem becomes severe in a direct way. Motion toward the nearest star cannot be thought of as a brief dash. It must be thought of as a passage measured in years at the absolute lower limit, and far more likely in decades, centuries, or longer at attainable speeds. Trajectory adds another layer to this difficulty. The nearest star is not standing still while the journey is underway. Neither is the Sun. Both stars move through the galaxy. A spacecraft aimed toward a nearby star cannot simply point toward where the star appears to be at launch and trust that position to remain correct. It must be sent toward where the target will be when the craft arrives. This is familiar in a modest way within the solar system, where missions are launched toward the future position of a moving planet rather than its current visible position. But across interstellar distance, the timescales are so long that the need for prediction becomes far more demanding. A journey lasting many years or many generations is not a crossing toward a fixed point. It is an attempt to intercept a moving star in a moving galaxy. Speed therefore matters not only in terms of how long the journey lasts, but also in terms of how precisely the long path must be shaped. A slower craft spends more time exposed to drift, error, and the cumulative consequences of tiny inaccuracies. Over short distances, a small misalignment may hardly matter. Over several light years, it can become decisive. A minute deviation in direction at departure can grow into an enormous miss. The path between stars is not marked by roads or stations. It is a narrow corridor of correct motion through a huge volume of mostly empty space. The slower the motion, the longer the correction problem must remain under control. Acceleration and deceleration shape the time of the journey as much as cruising speed does. A craft does not normally leap from rest to its full travel speed in an instant, and it cannot arrive usefully at a star if it merely rushes through the system without slowing. A serious journey, therefore, has at least 3 broad phases of motion. It must build speed, sustain motion through the long middle passage, and then shed speed again near the destination if arrival rather than flyby is the goal. Even if the middle phase is imagined in a highly idealized way, the opening and closing phases consume time and energy. The gulf between stars is so large that every part of motion matters. Relative speed also begins to change meaning at these scales. Inside human life, a difference of a few kilometers per hour is often trivial in spaceflight. The relevant differences become much larger, yet the same principle holds. A craft moving at a tiny fraction of light speed may be unimaginably fast compared with present-day vehicles and still require centuries for the trip. A craft moving at a larger fraction of light speed begins to reduce the journey to decades, but that still means long isolation in transit. Motion across the interstellar gap becomes a problem of fractions. Not fractions of human transport speed, but fractions of the fastest speed nature permits. Anything much smaller than that fastest speed leaves the journey stretched across enormous time. Time then becomes part of the motion rather than merely a consequence of it. For a short trip, travel time is an inconvenience. For an interstellar trip, travel time is one of the defining physical facts. It determines how long a machine must continue functioning, how long a course must remain accurate, how long any exposure to radiation or dust must accumulate, and whether the concept of a crew remains meaningful at all. Even in purely mechanical terms, before any discussion of a life support or psychology, a journey lasting decades or centuries ceases to resemble travel as ordinarily imagined. It becomes the prolonged maintenance of directed motion across a distance so large that the middle of the trip overwhelms the beginning and the end. The stars themselves reveal this slowness. Their positions change on the sky over long periods because they are moving relative to the sun. For astronomy, this motion is measurable and expected. For travel, it is a reminder that the crossing is long enough for the geometry of the local neighborhood to continue evolving while the craft is still en route. The destination is not only far away, it is receding or shifting across time according to its own galactic path. The journey is therefore not simply across distance, but through a changing arrangement of nearby stars. So the 7th region of this subject is motion through the gap itself. The interstellar gulf is large enough that speed loses much of its ordinary power to make distance feel small. Even very great speed remains modest beside a separation of more than 4 light years. A useful path must aim ahead of a moving target, remain precise over immense duration, and include both the gaining and losing of speed. Long before the question turns to what engines exist or what machinery can achieve, motion alone already makes the nearest star seem remote. The journey is not prevented first by imagination. It is enlarged beyond comfort by the sheer relationship between distance, speed, and time. When the nearest star is measured against today's spacecraft, the scale of the problem becomes much sharper. Human beings have already built machines that move faster than bullets, faster than planets orbit one another, and faster than anything ever used in ordinary transport. In the solar system, these speeds are extraordinary. They are enough to cross planetary distances, perform flybys, and leave the region of the giant planets behind. But interstellar distance changes the meaning of achievement. What counts as astonishing inside the Sun's domain can still count as slow between stars. The nearest star is so far away that the fastest machines humanity has made begin to look less like interstellar craft, and more like the first drifting objects at the edge of a much larger ocean. The fastest human-made object ever recorded is Parker Solar Probe. During its closest passes by the Sun, NASA states that it reaches about 430,000 miles per hour, or about 700,000 kilometers per hour. That figure is so large that it seems, at first glance, to dissolve the problem. A machine moving that fast appears almost beyond imagination. Yet this speed belongs to a very specific circumstance. Parker achieves it by falling deep into the Sun's gravitational well during a close solar pass. It is not cruising steadily toward another star at that rate with the ability to survive, navigate, and arrive usefully. Its record is real, but it is also local, tied to a path that swings through the inner solar system under the Sun's enormous pull. Even if one imagines, purely as a scale comparison, that a craft could somehow travel to Proxima Centauri at Parker's record speed for the entire crossing, the journey would still take roughly 6,600 years. That is longer than recorded history. It is longer than the age of written civilization in most parts of the world. It means that the fastest speed ever reached by a human-made object still does not reduce the trip to a span meaningful for a mission, a crew, or even a sequence of ordinary societies. The number is not a technological disappointment. It is a revelation of the size of interstellar distance. A speed that overwhelms the solar system still yields a journey measured in millennia when placed against the nearest star. A more relevant comparison comes from the craft that are actually departing the solar system, rather than diving close to the Sun. Voyager 1. The farthest human-made object is moving at about 38,000 miles per hour relative to the Sun, and NASA describes it as escaping the solar system at about 3.5 to 3.6 astronomical units per year. That is an extraordinary outward speed for a durable deep space probe. Yet if Voyager 1 were pointed toward Proxima Centauri, and the target were treated as fixed for the sake of a simple estimate, the crossing would still require about 75,000 years. NASA's current mission material and long-standing mission answers both support this general scale. The farthest machine ever sent by humanity remains, in interstellar terms, almost motionless. New Horizons offers another useful measure. NASA describes it as the fastest human-made object ever launched from Earth, leaving at about 36,400 miles per hour and later gaining additional speed through its Jupiter gravity assist. That launch energy was enough to reach Pluto far faster than earlier missions could have done, and it remains one of the clearest examples of what present-day launch systems can achieve when aimed for deep space. Yet when that speed is placed against Proxima Centauri, the result is still on the order of 78,000 years for the crossing. The fastest launch from Earth does not begin to turn the nearest star into a practical destination. It merely shows that present capability belongs to the scale of outer planet exploration, not to the scale of interstellar arrival. This comparison also reveals an important distinction between kinds of speed. Parker Solar Probe is the fastest relative to the Sun at its close approach. New Horizons is the fastest ever launch from Earth. Voyager 1 is the farthest outward traveller and one of the most relevant examples of long-duration deep space motion. Each machine represents a real technical triumph. Each shows a different way human engineering stretches motion outward from Earth. But none of them behaves like an interstellar ship in the fuller sense. None combines extreme sustained cruise speed, immense onboard endurance, shielding for the long medium between stars, and a credible means of slowing at another system. Today's fastest machines are masterpieces of planetary-era spaceflight. They are not yet true tools of travel between stars. The lesson is not that present spacecraft are unimpressive. It is the opposite. Their achievements are so great that they provide the clearest, honest benchmark. Voyager leaves the heliosphere. New Horizons reaches Pluto and beyond with unprecedented speed from Earth. Parker Solar Probe survives repeated passages through the Sun's outer atmosphere while setting the highest human-made speed ever recorded. If even these machines fail to make the nearest star accessible on useful timescales, then the obstacle is not a lack of effort or ingenuity in any simple sense. The obstacle is that current spaceflight is built for a solar system measured in hours, months, and years of robotic operation, while the nearest star demands a scale measured in thousands to tens of thousands of years at present-day speeds. So this eighth region of the subject settles on a hard comparison. Today's fastest machines are astonishing when judged within the Sun's realm. They can cross to the outer planets, leave the heliosphere, and survive environments once thought unreachable. But once they are placed against the nearest star, their greatness becomes a measure of the problem rather than its solution. The best machines humanity has yet launched do not fail because they are crude. They fail because the gap to another star is so immense that even the highest speeds ever achieved remain small before it. The nearest star is not waiting just beyond the outer planets. It stands at a distance that makes today's spacecraft look like the earliest and slowest beginnings of a much longer technological story. Chemical rockets are the oldest and most successful means by which human beings leave Earth and cross the solar system. They work by a simple physical rule. Matter is thrown backward at high speed, and the rocket moves forward in response. In chemical propulsion, the energy that drives this process comes from the bonds within fuel and oxidizer. When those substances react, hot gas is produced and forced through a nozzle, creating thrust. This method is powerful, direct, and proven. It is the reason spacecraft rise from launch pads, escape Earth's gravity, and begin their paths toward other worlds. Yet the same method that serves so well within the solar system reveals a severe weakness when the destination becomes another star. Chemical rockets are excellent at powerful departure. They are poor at sustaining the kind of extreme, long-duration speed that interstellar travel would require. The reason begins with energy. Chemical reactions release substantial energy by human standards, but they do not release enough per unit mass to make the exhaust speed extraordinarily high by interstellar standards. NASA Glenn explains rocket performance through specific impulse, a measure tied to how effectively propellant is used, and through the ideal rocket equation, which relates a rocket's change in speed to both exhaust performance and mass ratio. These ideas show that a rocket can only gain speed by either throwing exhaust faster or by carrying far more propellant compared with its final empty mass. Chemical propulsion can produce strong thrust, but its specific impulse remains limited because the exhaust velocity is limited by the energy available from chemical bonds. That is enough for launch, orbit changes, and planetary transfers. It is not enough to make another star seem close. This leads directly to the deepest burden of chemical rockets. A rocket must carry the propellant it intends to burn, but that propellant has mass, and that mass must also be accelerated. More propellant can produce more speed, yet the extra propellant also makes the rocket heavier at the start. NASA Glenn's mass ratio treatment lays out this structure clearly. The starting mass includes payload, structure, and propellant, while the ending mass is what remains after the propellant is gone. The ideal rocket equation then shows that the gain in speed rises only with the logarithm of this mass ratio. In plain terms, each further increase in desired speed demands disproportionately more propellant. The rocket begins to spend more and more of itself merely to move its own fuel. This is not a flaw in engineering detail. It is a consequence of the underlying physics of rocket motion. Inside the solar system, this burden can be managed because the required changes in speed, though very large by ordinary standards, remain within a range that staging, gravity assists, and careful mission design can handle. Chemical rockets can lift payloads from Earth, place them into orbit, and send robotic craft to the planets. They can even launch probes fast enough to leave the heliosphere over time. But the nearest star changes the scale so drastically that the same method begins to fail in a different way. The problem is no longer simply getting free of Earth or the Sun. The problem becomes building and carrying enough propulsive capability to shrink a journey of more than 4 light years into a meaningful time span. Chemical rockets, limited in exhaust performance, cannot do this without demanding impossible or near impossible mass ratios. A useful comparison makes the point quietly. NASA states that Voyager 1 is moving away from the Sun at roughly 17.3 kilometers per second. And NASA's educational material notes that at this rate, a voyage to Proxima Centauri would take more than 73,000 years. Voyager is not driven now by a continuously firing chemical main engine, but it is a product of the planetary-era mission architecture that chemical propulsion makes possible. Its speed, extraordinary within the history of spaceflight, still leaves the nearest star unimaginably far away in time. If a mission built on present-day chemical launch practice ends in a crossing time of tens of thousands of years, then the difficulty is not merely that rockets need refinement. It is that chemical propulsion belongs to the scale of planetary exploration, while the stars demand something far beyond planetary-era energy and mass economics. There is also the matter of arrival. A mission to another star is not truly useful if it only rushes through the target system at enormous speed without the ability to observe carefully, orbit, or stop. Chemical rockets struggle not only with acceleration but with the total budget of motion. A spacecraft must gain speed early, preserve its path over vast time, and then shed speed again if it is to do more than perform a brief flyby. Every stage of that plan requires propellant, and every kilogram saved for later braking must first be carried during the earlier acceleration. The rocket therefore suffers a layered penalty. Propellant for the end of the trip becomes dead weight during the beginning of the trip. In chemical propulsion, this penalty grows heavy very quickly. The fuel needed for arrival makes departure harder, and the fuel needed for departure makes launch still harder. Staging, which has been one of the great practical answers to the rocket problem, does help for launch from Earth. By discarding empty tanks and spent engines, a mission avoids carrying useless structure all the way through its climb. This principle is one reason chemical rocketry succeeds at all. But staging does not repeal the deeper limit. It softens the mass ratio burden for finite mission goals inside the solar system. It does not transform chemical propulsion into a practical way of reaching another star in one lifetime. Once the required change in speed becomes too large, even elegant staging meets the same wall. The chain of discarded stages becomes longer, the initial mass grows more extreme, and the delivered payload shrinks toward insignificance. A rocket architecture that is reasonable for moon missions, Mars missions, or even outer planet missions becomes disproportionate when asked to cross interstellar distance. Chemical rockets also reveal a mismatch between thrust and endurance. They're very good at producing a short, forceful push. NASA describes chemical propulsion as providing short, powerful thrust, which is exactly why it remains so valuable for launch and high-energy maneuvers. But interstellar travel does not mainly need a brief dramatic push in the way launch from Earth does. It needs a total mission architecture in which the gained speed is large enough to matter against light years of distance. Strong thrust by itself is not the answer if the underlying exhaust performance is too limited. A chemical rocket can be fierce for a short time and still leave the spacecraft on a trajectory that is glacial beside the gulf between stars. Power at departure is not the same as adequacy for the whole journey. So the ninth region of this subject settles on a hard but quiet conclusion. Chemical rockets are not failures. They are among humanity's greatest engineering tools, and without them, there would be no age of spaceflight at all. But their strength belongs to the solar system. Their energy comes from chemical bonds. Their exhaust performance is limited, and the rocket equation turns every demand for far greater speed into an overwhelming demand for propellant. Carrying more fuel makes the craft heavier. Reaching higher speed requires still more fuel. Slowing down at the far end deepens the burden again. By the time the nearest star is used as the destination, the logic closes in. Chemical rockets can lift, steer, and explore among the planets. They cannot make the stars near. Beyond chemical rockets, space engineering begins to imagine gentler but more efficient ways of moving through the dark. These methods do not rely mainly on the explosive release of chemical energy. Instead, they use electricity, reactors, or external beams to accelerate a spacecraft by other means. In broad outline, the promise is clear. A craft that uses propellant more efficiently can spend less of its mass on fuel and more on structure, instruments, or payload. It can continue thrusting for far longer than a chemical stage can burn. It can build speed patiently over months or years rather than in one brief violent push. This is why electric and nuclear propulsion occupy such an important place in any serious discussion of interstellar travel. They are not fantasies in the loose sense. They are real physical approaches that offer meaningful improvements over ordinary rockets. Yet once the nearest star is used as the destination, even these improved ideas begin to reveal how wide the gulf remains. Electric propulsion works by using electrical power to accelerate charged particles out of the spacecraft at very high speed. In ion propulsion, a noble gas such as xenon is ionized, meaning its atoms are stripped of electrons so that they become charged, and then electric fields accelerate those ions into an exhaust beam. NASA describes this method through the Dawn mission, whose ion engines made the mission possible and accelerated fuel to a velocity about 10 times that of chemical rockets. The difference is important. Chemical rockets produce strong thrust for a short time. Ion engines produce very low thrust, but they can continue for very long periods and use propellant with far greater efficiency. In the quiet arithmetic of deep space, long duration and high exhaust velocity matter greatly. A spacecraft that pushes gently for months can eventually achieve changes in speed that would be difficult for a chemical system carrying the same mass. This efficiency, however, comes with its own limit. Electric propulsion is not a sudden leap into interstellar capability. It exchanges force for patience. Dawn's ion engines are famously efficient, but their thrust is so small that the spacecraft would accelerate from rest to the speed of a highway car only over the course of days. That's perfectly suitable for a robotic mission crossing the solar system, where there is time to build speed gradually in the near vacuum of space. It is not, by itself, a way to make another star feel near. The journey to Proxima Centauri is so large that even a propulsion system far more efficient than chemical rockets still leaves the mission trapped inside the scale of long-duration robotic exploration, unless some much larger source of power is added. Electric propulsion improves the terms of motion. It does not erase the depth of the interstellar interval. Solar electric propulsion extends this same logic. Instead of drawing power from small onboard sources alone, it uses large solar arrays to convert sunlight into electricity, which then feeds electric thrusters. NASA's Solar Electric Propulsion Program presents this method as a way to extend the distance and duration of ambitious exploration and science missions. And NASA TechPort notes that advanced electric propulsion can increase transportation fuel efficiency by about 10 times over conventional systems. That is a serious gain. It means more mission for less propellant and a better ability to shape long deep space trajectories. But solar electric propulsion still depends on sunlight, and sunlight weakens with distance from the sun. That makes the method especially valuable in near solar system and inner deep space contexts, while leaving its usefulness diminished as a vehicle moves far outward. It is an elegant answer for many future missions among the planets. It is not a simple bridge to the stars. Nuclear propulsion enters the picture because it promises a denser source of onboard energy. NASA's space nuclear propulsion work divides this field into nuclear thermal and nuclear electric systems. In nuclear thermal propulsion, a reactor heats propellant directly and expels it through a nozzle, producing thrust with the specific impulse NASA describes as roughly double that of the highest performing traditional chemical systems. In nuclear electric propulsion, a reactor generates electricity that powers electric thrusters, combining nuclear energy with the efficient exhaust behavior of electric propulsion. These are substantial ideas, not slight refinements. They hold out the possibility of faster deep space missions, more capable cargo transport, and broader reach across the solar system. NASA and DARPA's Draco effort to demonstrate a fission-based nuclear thermal rocket shows that the concept has moved well beyond abstract speculation. Yet here again, the nearest star remains the stern measure. Doubling performance over chemical propulsion is important for missions to Mars and beyond. But interstellar distance is not merely a longer version of a Mars mission. It is a different scale of problem. A propulsion system that greatly improves travel within the solar system can still leave the nearest star profoundly far away. Nuclear thermal propulsion can shorten some deep space journeys. Nuclear electric propulsion can sustain efficient thrust for long periods. Neither of these gains, on its own, converts a crossing of more than 4 light-years into an ordinary mission span. They improve the architecture of space travel without abolishing the tyranny of distance. What appears revolutionary in planetary terms can remain modest in interstellar terms. Because onboard propulsion remains so burdened by propellant and mass, some of the boldest ideas try to move the power source away from the craft itself. Light sails belong to this class. In a sail concept, the spacecraft carries an extremely light reflective sail and is pushed not by onboard exhaust but by radiation pressure from light. Breakthrough Starshot presents one version of this idea, proposing gram-scale nanocraft driven by a powerful ground-based light beamer and aiming eventually for speeds around 1/5 of light speed. In pure distance terms, such speed would transform the problem. A probe at that velocity could cross to Alpha Centauri in roughly a few decades rather than in millennia. This is why the concept attracts so much attention. It is one of the rare proposals that genuinely reaches into the velocity range interstellar travel seems to require. But the cost of this apparent leap is severe. Starshot itself presents the effort as a proof-of-concept program, not as an already available transport system, and its challenge documents make clear that the sail, beam, navigation, and gram-scale payload constraints are all formidable. The proposed craft are extremely small. They're intended for flyby science, not for carrying human beings, large instruments, or braking systems capable of settling into orbit around another star. The very method that makes the speed conceivable also strips the mission down to something fragile and minimal. It is not a starship in the ordinary imaginative sense. It is a tiny messenger fired across the dark at extraordinary speed, with major unanswered engineering challenges still in front of it. So this 10th region of the subject settles into a sober middle ground. Electric propulsion is real and highly efficient. Solar electric systems extend mission reach within the Sun's realm. Nuclear propulsion promises a deeper reserve of performance and may reshape future travel across the solar system. Beamed light sail concepts reach farther still in theory and begin to touch truly interstellar speeds for tiny probes. Each of these ideas is more capable than ordinary chemical rocketry in some important way. Each narrows the gap between current practice and interstellar ambition, and yet the nearest star continues to stand beyond easy reach. The better engines are real. The abyss is real as well. Even advanced propulsion concepts improve the journey less by making the stars near than by revealing how much more than better engines the stars demand. A journey to the nearest star is not blocked by distance alone. It is blocked by the energy needed to fight that distance in a meaningful way. Once the discussion moves beyond ordinary spacecraft and beyond the limits of chemical fuel, the problem narrows into a simpler and harder form. How much energy must be gathered, stored, directed, or delivered to a craft so that the crossing is not measured in thousands of years? At this depth of the subject, propulsion becomes less about engines in the mechanical sense and more about energy in the physical sense. Motion across interstellar space is expensive before it is difficult in any other way. The price is written first in energy. This becomes clear as soon as speed is treated honestly. A small increase in velocity can shorten a journey. A much larger increase can shorten it far more. But the energy required to make an object move does not rise in a gentle straight line. At ordinary speeds, the kinetic energy of motion rises with the square of speed. If the speed is doubled, the energy is not merely doubled, it becomes 4 times larger. If the speed is increased by a factor of 10, the energy becomes 100 times larger. This is a quiet law with enormous consequences. It means that the transition from a slow spacecraft to a truly fast interstellar craft is not a matter of adding proportionally more power. It is a matter of crossing into an energy demand that swells much faster than intuition expects. Within the solar system, this rising cost can still be tolerated because the required speeds, while high, are not pushed toward the deeper extremes. Missions are planned around years, not around fractions of light speed. Interstellar travel changes the frame. If a craft moves at only a tiny fraction of the speed of light, the trip to the nearest star still lasts centuries or millennia. To bring the crossing into decades, the craft must move at a substantial fraction of light speed. At that point, the energy demand becomes severe even before the special demands of shielding, guidance, or braking are counted. The faster the craft is meant to go, the more energy must be paid merely to place that mass into motion. Mass is the next decisive term. The energy needed depends not only on speed but on how much material is being accelerated. A gram-scale probe is one thing, a robust robotic observatory is another, a human vehicle with shielding, life support, redundancy, supplies, and long-term survivability is something else again. Every kilogram added to the craft becomes a kilogram that must be pushed to high velocity and, if arrival matters, later slowed down again. This is why many of the boldest interstellar concepts shrink the payload to something almost microscopic. The smaller the mass, the more conceivable the energy budget becomes. The larger the ambition, the more brutally the budget expands. Braking deepens the burden. It is tempting to think only of launch, only of the energy needed to send a craft outward. But a useful mission to another star does not ideally end as a blind projectile racing through the target system. It must arrive with the ability to slow, observe, perhaps orbit, perhaps land, perhaps communicate over time. Every unit of speed gained early must later be removed unless the mission is satisfied with a rapid flyby. In the simplest sense, this means the energy problem appears twice. One large energy demand is needed to accelerate. Another large demand is needed to decelerate. If the craft carries its own braking system, then the mass of that system must itself be accelerated during the first half of the journey. The energy problem therefore folds back on itself. Power and energy are related but not identical, and interstellar travel suffers from both. Energy is the total amount required. Power is the rate at which that energy is delivered. A spacecraft may, in principle, need an immense total energy budget even if it acquires speed gradually over time. But if the mission calls for rapid acceleration, then the power requirement grows huge as well. A system that can eventually supply enough total energy may still fail, because it cannot deliver that energy at the rate the mission demands. This distinction matters because it separates the dream of a large energy reservoir from the reality of an engine or beam able to act with sufficient force. A deep reservoir without enough power leaves the craft accelerating too slowly. Great power without enough total energy leaves it unable to sustain the effort long enough. Interstellar flight needs both in daunting measure. Storage creates another difficulty. Energy can be produced externally, as in a beamed sail concept, or internally, as in a reactor-based craft. But either path has consequences. If the energy is stored on board as fuel, then the storage system adds mass, and the vehicle must carry its own burden. If the energy is delivered from afar, then the transmitting system must be extraordinarily powerful, accurate, and sustained over long duration. Neither path is free. The first suffers from the tyranny of carried mass. The second suffers from the scale and precision of the external infrastructure. The nearest star remains distant enough that any realistic energy solution becomes a civilization-scale undertaking, rather than a simple extension of ordinary engineering. Waste heat makes the problem still quieter and still harder. Engines are never perfectly efficient. Whenever energy is transformed, some part of it becomes unwanted heat. On Earth, machines shed heat into air or water. In space, there is no surrounding air to carry heat away by convection. A spacecraft must radiate excess heat into the cold by electromagnetic emission, and that is a slower and more demanding process. The more powerful the engine or onboard system, the more serious the thermal burden becomes. A craft meant for interstellar speed would not only need extraordinary energy, it would also need a way to survive the heat generated while using that energy. This turns propulsion into a thermal problem as much as a motion problem. At very high fractions of light speed, the difficulty deepens again because the simple ordinary expression for kinetic energy no longer tells the whole story. Relativity becomes important. As speed approaches the speed of light, the energy required to continue increasing that speed rises more harshly. Nature does not merely discourage light-speed travel for material objects, it forbids it. The speed of light is not a milestone waiting to be reached by a strong enough engine. It is a limit built into the structure of space-time. This means that interstellar flight cannot solve its problem by simply pressing ever closer to perfect speed without paying an increasingly extreme energetic cost. The nearer a craft tries to move toward that ultimate limit, the more punishing the price becomes. So the 11th region of this subject reaches the hidden heart of the journey. The nearest star remains far not only because the gulf is long, but because useful speed across that gulf requires immense energy, and immense energy multiplies every other burden. The craft must be accelerated, its mass must be kept low, or the energy budget grows unmanageable. If it is to arrive rather than merely pass through, it must shed speed again. The system that provides the energy must either be carried or supplied from afar. Much of that energy becomes heat that must be endured and released, and if the craft aims for the high fractions of light speed that make interstellar travel seem timely at all, the energetic demand rises into a realm that stops resembling ordinary transport and begins to resemble the total effort of a civilization. Distance remains the outward fact. Energy is the inward cost that gives that fact its full weight. The journey between stars is hazardous not because the space is crowded, but because the traveller must endure that thin environment for so long and, if it moves fast enough to make the trip meaningful, must strike that environment with extraordinary violence. In the quiet scale of the solar system, a spacecraft can survive years of exposure and occasional impact because the mission remains comparatively short and the speeds remain within the range that current shielding and engineering can tolerate. Interstellar travel changes both terms at once. The duration grows immense, and the desired speed rises toward levels where even faint matter becomes dangerous. The road itself begins to behave like an enemy, not because it is dense, but because time and velocity turn rarity into consequence. Radiation is one part of that danger. Outside the protection of Earth's atmosphere and magnetic field, space contains energetic particles that can pass through living tissue and into machinery. NASA describes space radiation as one of the most hazardous aspects of human spaceflight, and ESA notes that cosmic radiation can damage the body in ways that include increased cancer risk and injury to the brain, heart, and central nervous system. In deep space, this exposure does not come as one dramatic flash alone. It is a steady and cumulative burden, mixed from galactic cosmic rays, solar particle events, and other energetic sources. A short mission can sometimes tolerate a limited dose. A mission lasting decades or longer turns that dose into a governing condition of the voyage. Machines suffer as well. Energetic particles can degrade electronics, upset computer systems, and damage materials over time. ESA's descriptions of radiation hazards note that charged particles threaten satellites through short circuits and other severe malfunctions, while NASA's radiation program treats the protection of crews and systems as an ongoing technical challenge rather than a solved matter. A spacecraft intended for interstellar travel would not only need to survive launch and operation, it would need to preserve its memory, sensors, power systems, and control logic through a relentless particle environment for spans far beyond ordinary missions. In that setting, reliability is no longer just a matter of careful design. It becomes a prolonged contest with invisible damage accumulating year after year. Dust creates a different kind of threat. The interstellar medium contains tiny solid grains as well as gas, and NASA's Stardust work confirms that actual interstellar dust particles pass through and can be collected for study. On quiet scales, these grains seem insignificant. They are microscopic, sparse, and almost weightless by everyday standards. But a collision is not judged by size alone. It is judged by relative speed. When a spacecraft moves through the interstellar medium at a high fraction of the speed of light, even a minute grain can strike with destructive energy. What is harmless to a drifting object becomes dangerous to a fast one. The emptiness between stars therefore hides a field of potential impacts, most of them tiny, none of them trivial at sufficient speed. This is one reason high-speed interstellar concepts must treat the front surface of the craft almost like armor. breakthrough. Starshot's technical challenge discussions note that a protective coating is required for dust collisions and erosion caused by atomic particles in the interstellar medium. The same research forum estimates that over a journey to Alpha Centauri, each square centimetre of frontal area could encounter many impacts from submicron dust, with a smaller but still real chance of collisions with larger particles. Those numbers do not describe a thick storm. They describe a sparse medium encountered across a very long path. Yet that is enough. A few dangerous impacts are sufficient when the craft is tiny, fragile, and moving at extreme speed. Interstellar travel does not need dense debris to become hazardous. It needs only long exposure and tremendous velocity. Gas itself contributes to erosion. Single atoms or ions in the interstellar medium carry little threat to a slow-moving craft, but at very high relative speed they become a continual abrasive flow. Over time they can strip material from exposed surfaces, charge structures electrically, and add to the thermal and mechanical burden on the leading edge. Starshot's challenge material explicitly pairs dust collisions with erosion caused by atomic particles, which shows that the hazard is not limited to rare larger strikes. The road wears the craft down grain by grain and atom by atom. A mission that aims for truly interstellar velocity must therefore survive not just a few dramatic impacts, but an unending sequence of smaller assaults, whose cumulative effect can also be mission-ending. The severity of both dust and radiation depends strongly on speed. A slow probe crossing the gap over tens of thousands of years faces long exposure but relatively modest impact energies. A fast probe reduces travel time but greatly intensifies each collision. This is the cruel exchange at the heart of the road hazard. To make the journey short enough to matter, the craft must move fast. To move fast is to make the medium more violent. The very solution to the problem of time deepens the problem of impact. Breakthrough Starshot attracts attention because it reaches into the range of about 1/5 of light speed for gram-scale nanocraft. But the same official concept and challenge documents make clear that cruise protection is then a central engineering issue, not a minor afterthought. For living passengers, these hazards become more severe still. Radiation that threatens electronics also threatens tissue, and shielding against it adds mass, which then makes propulsion harder. Shielding against dust and gas impacts also adds mass, and the leading surfaces must be stronger, thicker, or sacrificial in some way. Every layer of protection makes the spacecraft heavier. Every increase in mass demands more energy. The road therefore punishes both fragility and protection at once. A lightly built craft risks erosion and penetration. A heavily shielded craft becomes harder to accelerate to useful speed. This does not make interstellar travel impossible in principle, but it reveals why the journey itself cannot be treated as a simple empty crossing. The medium is thin, but it forces hard design choices all the way down. So the 12th region of this subject settles on the hazards of the road. Between the Sun and the nearest star lies a medium too thin to see as weather, and too real to ignore as nothing. It carries radiation that damages bodies and machines. It contains dust grains that become dangerous at high speed, and atomic particles that erode exposed surfaces over time. The faster the craft travels, the more violent the encounter becomes. The longer it travels, the more cumulative the damage grows. This is why the gulf between stars is not only a problem of propulsion and energy, it is also a hostile passage whose faint substance turns into a sustained assault. The nearest star remains far away not only because the distance is immense, but because the path itself resists being crossed. A spacecraft bound for another star would not fail only because of speed or energy. It would also face the quieter problem of lasting long enough to use whatever speed and energy it has been given. A mission across interstellar distance is not a moment of launch followed by a simple glide. It is an extended state of operation that must continue without interruption through years, decades, centuries, or even longer, depending on the design. During that time, the craft must remain pointed, powered, aware of its own condition, and able to correct small errors before they grow into fatal ones. The machine must keep functioning not merely as an object moving through space, but as a self-consistent system whose parts continue to support one another over spans far beyond most engineering experience. Guidance is the first quiet requirement. To reach another star, a spacecraft must not only move quickly, it must move accurately. The target is distant, and distance turns small angular errors into large positional failures. A slight misalignment at departure can become an enormous miss after several light years of travel. This means that the spacecraft must know where it is pointed, how that direction changes with time, and how to adjust when reality departs from the plan. Stars shift slowly in relation to one another. The spacecraft itself may rotate, drift, or experience tiny forces from uneven heating, particle impacts, or internal motion. None of these effects may seem large in the moment. Over a long enough voyage, all of them matter. Navigation in such a mission would depend on continuous orientation against the sky and continuous discipline in onboard measurement. A craft cannot rely on roads, landmarks, or frequent external correction. Signals from Earth would take years to arrive and years to return. Even if communication remains possible, it would not provide immediate steering in the ordinary sense. The spacecraft must therefore carry a large part of its own guidance logic within itself. It must measure stars, track inertial motion, compare present conditions with its intended path, and decide when correction is necessary. In a long interstellar mission, guidance becomes a form of long-lived memory. The machine must remember what it is trying to do and retain the ability to keep doing it without constant help. Small correction is as important as large propulsion. A path launched perfectly would still not remain perfect forever. Tiny deviations accumulate. A minute force acting over years can shift a trajectory significantly. This means that some means of course adjustment is required, whether through small thrusters, sail control, beam steering, or some other method suited to the craft. But every correction system introduces another burden. It requires power. It requires moving parts or controlled surfaces or precise field behavior. It may require stored propellant. The machine that must survive long enough to reach another star is therefore not just a projectile, it is an enduring navigator, and endurance in navigation always depends on parts that can fail. System failure becomes more severe as mission length grows. On a short mission, engineers may accept limited redundancy because the spacecraft only has to survive for a known interval. On an interstellar mission, every component must be judged not merely by how well it works at first, but by how long it can continue to work under radiation, temperature cycling, material fatigue, and cumulative exposure to the interstellar environment. A sensor may slowly degrade. A power system may lose efficiency. A memory device may suffer corruption. A seal may weaken. A cable may embrittle. Lubricants, if any are present, may age or migrate. Surfaces may erode. The challenge is not one dramatic accident alone. It is the slow wearing away of certainty. Redundancy helps, but only to a point. A second copy of an instrument can preserve function if the first fails. Multiple processors can vote against corrupted outputs. extra pathways can preserve power flow when one route is damaged. These methods are already central to spacecraft design. Yet redundancy is not magic. Every duplicate part adds mass. Every additional subsystem adds complexity. Complexity itself can become a source of failure if the craft contains too many interactions to manage cleanly. There's always a tension between simplicity and resilience. A simple system has fewer things to break. A redundant system can survive more breakage. Interstellar travel forces these two virtues into constant negotiation. Maintenance is even harder. On Earth, a machine lasts because people inspect it, replace worn parts, tighten connections, patch leaks, and correct problems before they spread. In orbit near Earth, astronauts can sometimes repair equipment directly. In the distant solar system, repairs become rare and difficult, and robotic missions are generally built to function without physical intervention. Interstellar missions push this logic much farther. No technician will board the craft in transit. No spare module can be launched to meet it easily. No immediate rescue is possible. If something breaks, the spacecraft must either repair itself, isolate the failure, or continue in reduced form. This turns maintenance into an internal capability rather than an external service. The machine must be, to some degree, its own mechanic. Self-repair sounds simple in language and difficult in reality. It could mean many things. It could mean switching automatically to backup systems. It could mean reconfiguring software around damaged hardware. It could mean using modular structures that can be electrically bypassed when one segment fails. In more ambitious concepts, it might even mean robotic manipulation of parts, internal manufacturing, or the use of reserve materials to rebuild damaged sections. Every increase in self-repair capacity, however, also increases the mass complexity and internal demand of the spacecraft. A craft that can truly maintain itself across generations of operation begins to resemble a small autonomous ecosystem of machinery rather than a simple vehicle. Power reliability sits underneath all of this. Guidance, communication, sensing, correction, thermal control, and memory preservation all depend on power. A short mission may survive a temporary power problem. A centuries-long mission cannot tolerate prolonged weakness. Solar panels lose usefulness far from the sun unless the mission remains within an externally illuminated architecture. Batteries alone are storage devices, not enduring sources. Radioisotope systems last for long spans but steadily weaken. Reactors promise longer and stronger output but add mass, shielding demands, and their own failure modes. Whatever the source, the deeper truth remains the same. A spacecraft that cannot keep power flowing cannot keep itself coherent. Communication is part of reliability as well, though not in the ordinary sense of constant conversation. Over interstellar distance, communication becomes delayed, faint, and dependent on extreme precision in pointing and reception. A craft may continue to function even if contact is lost, but from the perspective of the mission, silence is a kind of partial failure. The farther the spacecraft travels, the more challenging it becomes to send usable data home and to confirm that the mission remains alive. Reliability is therefore not only survival, it is the continued ability to be known. So the 13th region of this subject settles on the endurance of the machine. A voyage to another star demands not just propulsion, but guidance that remains accurate over immense distance. Systems that resist slow decay. Correction mechanisms that survive long use. Redundancy without crippling complexity. Some degree of internal maintenance, and power that continues to support the whole structure for spans far beyond ordinary engineering life. The problem is not only reaching interstellar speed, it is remaining a functioning spacecraft long enough for that speed to matter. The nearest star is not unreachable simply because the gap is long. It is unreachable because the machine that attempts the crossing must remain trustworthy while crossing it. And trust is one of the hardest things to preserve over time. For a human being, the distance to another star is not measured only in kilometers, light years, or propulsion limits. It is also measured in lifetime. A journey can be physically possible in the narrow sense that matter may cross the gap, and yet remain humanly unreachable because the span of travel exceeds the length of a life. This is where the problem becomes different again. The stars are not only far from Earth, they are far from the body's natural duration, far from the rhythm of memory, far from the continuity of a single mind moving from departure to arrival. At this depth of the subject, interstellar travel stops looking merely like difficult transportation and begins to look like a confrontation between cosmic scale and human time. Human life is brief when placed beside the distances between stars. Even a long life, healthy and full by ordinary standards, occupies only a small interval. The body grows, matures, ages, weakens, and ends within a span that is meaningful on Earth, and tiny in astronomical terms. A mission lasting decades might already consume most of one adult lifetime. A mission lasting longer than that begins to turn the traveller into a witness of the journey, rather than a participant in a full mission arc. Departure may be experienced directly, but arrival may belong to old age or may never be seen at all. This changes the emotional and practical meaning of travel. A voyage that does not fit inside one life ceases to resemble a journey in the ordinary human sense. This problem is not solved simply by preserving the body in transit. Human beings are not only biological organisms that must remain alive, they are also conscious beings who live through time in a particular way. Life unfolds through wakefulness, habit, expectation, memory, attachment, and change. A mission lasting many decades would impose a life defined almost entirely by enclosure, procedure, and prolonged separation from the world of origin. A mission lasting centuries would go beyond even that. It would no longer ask one generation to endure a difficult expedition. It would ask many generations to inherit an unfinished path. The ship, if it carried people, would become not merely a vehicle, but a world of succession. Generation ships enter thought at exactly this point. The idea is simple in outline. If no single crew can live long enough to see arrival, then the mission might continue through descendants born aboard the vessel. In that case, the travellers who depart would not be the travellers who arrive. The journey would be handed forward from parents to children and from children to their own descendants. Interstellar travel would cease to be a mission completed by its founders and become instead a social lineage carried through time. This changes everything. The central problem is no longer only propulsion. It is the long survival of a functioning human community under confinement, isolation, and inherited purpose. Such a community would need more than food, air, water, and radiation protection. It would need coherence, it would need institutions, education, conflict management, reproductive stability, technical continuity, and a reason for later generations to accept obligations they did not choose at departure. The first crew may volunteer freely. Their descendants would simply awaken into the mission as the condition of their existence. For them, the ship would not feel like transportation in the original sense. It would feel like the only world they have known. The destination, distant and unseen, would be more like an inherited idea than a personally chosen goal. This is one of the deepest human barriers to interstellar travel. A long enough voyage turns intention into tradition, Biology adds its own constraints. Human beings require not only oxygen, water, and food, but gravity or something that substitutes for some of its effects, protection from radiation, stable developmental conditions for children, and a medical system capable of responding to disease, injury, pregnancy, aging, and psychological strain over very long spans. Short missions stress the body in ways that are already well studied. Long missions would magnify every concern. Bone loss, muscle loss, immune change, altered development, and cumulative radiation exposure become more serious when the mission no longer lasts months but years or generations. A vessel carrying people across interstellar distance would not merely transport bodies. It would have to sustain a complete and durable biological environment. Psychology may be even more difficult than biology. Human minds are shaped by variation, horizon, novelty, landscape, weather, relationships, and the sense that effort is connected to outcomes within a visible frame of time. A closed interstellar habitat would restrict many of these conditions. The sky would not change in the familiar way. The ground would not exist. The community would be small. Departure from the habitat would be impossible. Return would be impossible in any meaningful sense. Time would stretch strangely. For the first generation, life would be defined by the memory of Earth and the knowledge of permanent separation. For later generations, the challenge would be different. They would inherit confinement without memory of any larger world. In either case, the mission would demand a kind of long psychological steadiness, unlike anything human societies have yet sustained in isolation. There is also the matter of culture. A human voyage lasting longer than a lifetime would not preserve a single unchanged social order. Language would shift. Values would shift. Systems of authority might change. Technical knowledge would need to be taught, retained, and refreshed with extraordinary care. A generation ship could not assume that the meanings held by its founders would remain intact after many decades or centuries. This matters because the mission depends on continuity. If later generations decide the destination is irrelevant, or if they lose the knowledge required to operate the vessel safely, the voyage ceases to be what it was meant to be. Interstellar travel at human scale therefore becomes partly a problem of historical stability. The ship must carry not only bodies and machines, but a civilization small enough to travel and stable enough to endure. Suspended animation is sometimes imagined as a way around these difficulties, but at present it remains speculative for human interstellar use. The desire behind the idea is understandable. If the body and mind could be paused safely for long durations, then the journey might fit within one subjective lifetime even if it did not fit within one ordinary lifespan. But a concept is not a capability. No accepted present method allows healthy human beings to be placed into long suspended transit and restored after decades or centuries with mission-ready reliability. So the problem of human time remains largely what it is now. The body ages, consciousness continues, and long travel remains long life. This is why robotic missions appear more realistic than human missions whenever another star is discussed seriously. A machine does not age in the human sense, though it degrades in other ways. It does not suffer loneliness as a person does. It does not require a social world in order to remain itself. A probe can succeed even if it never feels the journey at all. But the section here concerns human beings, and for human beings the obstacle is not only whether a craft can cross the gap, it is whether a human life can still meaningfully belong to that crossing. The farther the journey extends beyond one life, the less it resembles exploration by travellers, and the more it resembles the transport of an enduring community or a message passed through generations. So the 14th region of this subject rests within human time itself. The nearest star remains far away because the journey does not fit naturally inside the span of one life. A long mission strains the body, the mind, and the social fabric that makes human endurance possible. A generation ship transforms travel into inheritance. A closed habitat must become a complete living world. Culture must remain coherent across decades or centuries. Biology must be protected from confinement, radiation, and long-term fragility. Psychology must survive monotony, separation, and altered meaning. Even before the ship reaches another star, the mission has already demanded that human life itself be reorganized around a duration for which it was never evolved. At the deepest point of this subject, the nearest star remains unreachable not because of one dramatic prohibition, but because several ordinary truths of physics join and reinforce one another until they form a single enduring barrier. Distance is the first truth. More than 4 light-years separate the Sun from the nearest star. That fact alone does not make travel impossible in the strictest abstract sense. Matter can cross distance. Light crosses it every day. But the second truth follows immediately. Light is the fastest thing nature allows, and even light requires years for the crossing. A material craft must move more slowly. So the journey begins already stretched beyond immediacy, beyond ordinary transport, and beyond the scale on which human effort usually remains meaningful. Speed appears to offer relief, but speed brings the third truth. Great speed demands great energy. The faster the craft must travel, the more severe the energetic cost becomes. This is not a social inconvenience and not a temporary weakness of present engineering. It is built into motion itself. A small probe requires energy. A larger robotic craft requires much more. A human-carrying vessel, with structure, shielding, life support, and redundancy, demands far more again. If the mission is to arrive usefully rather than merely pass through, the burden doubles in spirit because the craft must not only gain speed, but lose it at the far end. The journey to the nearest star is therefore never just a problem of departure. It is a problem of departure, crossing, and arrival, each one drawing on the same deep reserve of physical cost. Propulsion then introduces the fourth truth. No engine is judged only by how forceful it seems in isolation. It is judged by how much mass it must push, how efficiently it uses propellant, how long it can sustain action, and what penalties it imposes on the craft that carries it. Chemical rockets are too limited by propellant and exhaust speed. Electric propulsion is more efficient, but gentle and slow. Nuclear concepts promise more, but still do not make the crossing easy. Beam sail ideas reach toward more suitable velocity, but only by shrinking the payload and leaning on extraordinary external infrastructure. Every proposed improvement helps one part of the problem while leaving the larger shape intact. Better engines do not erase the abyss. They only show more clearly which part of the abyss yields and which part remains. Then the road itself speaks. Interstellar space is thin, but not absent. Gas, dust, magnetic field, and radiation fill the gulf in faint measure. At low speed, that thinness seems merciful. At high speed, it becomes dangerous. Tiny grains become projectiles. Atomic particles become erosive. Radiation accumulates through time. The very act of moving fast enough to make the journey short also makes the environment more violent. This is one of the quiet cruelties at the center of interstellar travel. The solution to the problem of duration deepens the problem of damage. A slow craft suffers long exposure. A fast craft suffers harder impact. The medium between stars is not dense enough to block the journey outright. but it is real enough to punish every serious attempt. Time deepens everything still further. A machine that travels toward another star must remain functional for far longer than most human systems are asked to endure. Guidance must remain accurate. Memory must remain intact. Power must continue. Sensors must survive. Corrections must be made after years of drift and exposure. Small failures can become fatal because there is no nearby repair, no practical rescue, and no quick exchange with Earth. The craft must carry within itself the means to remain coherent. Interstellar travel is therefore not only about creating motion, it is about preserving order over time. The longer the crossing lasts, the more the problem shifts from propulsion to endurance. For human beings, the final truth is harsher still. Human life is short beside the scale of the stars. A journey that might be possible for matter may still be inaccessible to a civilization shaped by finite bodies, fragile minds, and generations that do not naturally inherit one mission unchanged. A robotic probe can endure silence without loneliness and can drift without boredom. A human voyage would demand far more than a strong hull and a powerful engine. It would require a stable biological habitat, protection from radiation, social continuity, psychological resilience, and a cultural structure capable of surviving confinement across spans that may outlast the founding generation. The journey would no longer be travel in the familiar sense. It would become a transferred purpose, a society in transit, or a life spent mostly between worlds. At this deepest level, the nearest star remains far because every layer of difficulty multiplies the others. More shielding adds mass. More mass demands more energy. More energy creates more heat and greater engineering burden. Greater speed reduces travel time but intensifies collision risk. Longer mission duration reduces impact severity only by extending radiation exposure, system fatigue, and generational strain. Improved propulsion may solve one narrow term while worsening another. No single obstacle stands alone. Distance, energy, speed, shielding, reliability, biology, and time form one interlocked structure. This is why the challenge feels so resistant. The stars do not refuse approach through one locked gate. They remain distant because the whole path is built from many gates that stand close behind one another. And yet this does not reduce the nearest star to fantasy. It remains a real place, measurable, luminous, and physically connected to the same galaxy as the Sun. Its light arrives, its planets, if present, circle in accordance with the same gravity that governs the solar system. Nothing about the nearest star is unreal or mystical. The difficulty lies not in the destination, but in the relationship between that destination and the scale of human means. Nature permits knowledge of the star far more easily than arrival at it. Astronomy reaches there with light, spectroscopy, timing, and inference. Travel must reach there with mass, energy, structure, and endurance. Knowledge crosses first because light carries it freely. Bodies do not. So the final limit of reach is not a single sentence of defeat. It is a recognition of proportion. The nearest star belongs to the same universe as Earth, yet it stands at a distance where the ordinary tools of travel fail. Advanced tools remain burdened, and even the strongest imaginable missions are forced into terms measured by decades, centuries, or more. The destination is near on the scale of the Milky Way, and far on every scale that shapes a human journey. That is why the nearest star is still too far. It is not hidden. It is not forbidden by mystery. It is simply placed across a gulf so large, and across a set of physical demands so deep, that the dream of going there remains greater than any practical road now known. The nearest star remains where it has always been, shining steadily across the dark, close enough for its light to reach Earth, and far enough that the crossing still resists the full weight of human intention. In the long quiet view, this distance does not feel hostile. It feels exact. Space is large, matter is finite, time is costly, and every journey must answer to those conditions. The stars do not bend toward desire. They remain arranged by gravity, motion, and scale, indifferent to impatience and unchanged by hope alone. So the thought comes to rest with the simple image. The sun moves through its calm local region of the galaxy, carrying Earth and the other worlds with it. Beyond that familiar household lies the wide interstellar dark, thin with gas and dust, marked by radiation, and stretched across years even for light. Far beyond that dark waits another small sun, not unreachable in imagination, but still remote in the deeper language of energy, endurance, and time. It is there. It remains real. It continues to shine whether or not anything made by human hands ever crosses the gulf. For now, knowledge travels more easily than bodies. Telescopes gather light. Instruments measure motion. Careful reasoning turns faint signals into understanding. The journey of thought goes farther than the journey of machines, and that too is a form of arrival. It does not place a vessel in orbit around another star, but it does allow the distant point to become part of the known universe. And in that quiet limit there is a certain calm. The nearest star does not need to be near in order to matter. Its distance gives shape to the scale of the cosmos and to the small bright world that considers it from afar. The gap remains, the light arrives, the mind follows, and then slowly returns home through the dark.